Okay. So today we're going to start talking about binary trees. So these are done in the context of, let's add a slide here, nonlinear linked data structures. All right, so nonlinear linked data structures. These are, as opposed to linked lists, stacks, and queues, these are nonlinear, which means that every node potentially can have more than one child node. All right, so we can link to more than one node. Examples of these are binary search tree, BST. And then off this guy, we have AVL trees, red-black trees. And we'll at least talk about those in passing. We'll see how we're doing on time, whether or not we implement either of those. We also have something called a graph. And we're going to use graphs to explore the traveling salesman problem. TSP, it's a famous computer science problem thingy. We also have n-ary trees, as opposed to binary. N-ary, binary is 0, 1, or 2 children to a node. N-ary says 0 or more children to a node. All right, so let's just leave the list starting with this, but our change in thinking now is moving down this path of being nonlinear. We don't just have one node linked to exactly one other node. We have multiple nodes at play here, okay? So let's draw a picture of what a binary tree looks like. I'm just making up values here. And actually, let me just go back to the slide before this. I'll say binary trees. And binary search trees are an example of these guys. And AVL and red-black trees are examples of binary search trees. And we'll talk about the difference here in a few minutes. All right, let's just make a couple more copies here. Stretch this out a bit. Yeah, let's go one more level. Something like that. All right, so this could be a binary tree. Where each node has at most 2 children. All right, so this would describe for us a generic binary tree. Now, binary trees in and of themselves aren't all that useful. It's just describing that first step of a nonlinear linked data structure. So now, if we wanted to take this and say, well, we're actually going to use this as a search tree. Again, each node has at most 2 children, and we follow the binary search tree rules, which state all nodes, let's see, all children, all child nodes, yeah, all child nodes to the left of a node hold values less than or equal to the node. All child nodes to the right of a node values greater than the node. Okay, so far this is not a binary search tree. If we wanted to make this guy a binary search tree, let's do this. We have to think about how are things added to a tree. So we start off with an empty tree, and then we add our, so initially we have an empty tree. We add our first node. Well, we have nothing in the tree, so we just add it right there. Next thing, we can pick the next node we're going to add. You will end up with different trees depending on the order in which you added things. All right, that's where these next 2 things come into play. These guys are examples of what's called a self-balancing tree, because there's a decent chance, I'm off center here. Oh, my phone. Ninja. See, look, I'm a mess. Ish. All right. So a binary tree really has no order to it. A binary search tree has rules associated with it that dictate order, and we're going to be looking at that today. But depending on the order in which things were added, you could get a tree that's kind of lopsided, right? You could even get trees that are very, very, very lopsided, which then become less and less efficient when we think about searching them. So these algorithms like ABL trees or red-black trees, these guys are what are called self-balancing binary search trees, where after you enter something into the tree, you ask the question, is this tree out of balance? Is it lopsided? Is one side greater than one level deeper than the other side? If so, I need to go ahead and make a chiropractic adjustment to the tree to get it back into balance. Okay, which is complex and resource intensive. I mean, it takes quite a bit to do that, but it is something that we would say if you have data that, if you have large sets of data that needs to be searched quickly, and maybe that data doesn't change that often, the juice might be worth the squeeze type thing. It might be worth that extra effort to keep it in balance. All right. So binary tree, no rhyme or reason other than every node can have at most 2 children. Not that useful. Binary search tree follows these rules, and the tree will change probably depending on the order in which you add things. So let's go ahead and add this 8. So if you've ever seen, is it The Price is Right that has the game Plinko, where you drop the thing in the top and it. So we want to kind of think about that. We're going to take this 8 and we're going to drop it onto the top of the tree. Well, it can't go here because that place is already reserved, right? So we're going to say, is an 8 less than or equal to a 1, or is an 8 greater than a 1? Greater than. So we're going to put it to this side. Then we say, we found a nice little plot of land for it. We'll drop it right there. All right, then we'll take our 2. is the spot is taken. Is a 2 less than or equal to a 1, or is a 2 greater than a 1? It's greater than, so we'll drop it here. Is a 2 less than or equal to an 8, or is a 2 greater than an 8? Less than or equal to, so we'll end up placing it right here. Then we could take our 0. So 0, we don't have a space here. Is a 0 less than or equal to a 1, or is it greater than 1? It's less than or equal to. So we can go ahead and place it there. Then we'll take our 12, drop it. Can't fit here. Is it less than or equal to, or is it greater than? It's greater than. Can't fit it here. Is it less than or equal to, is it greater than? It's greater than. I can fit it right here. Let's go with our 4. Can't fit it here. Is it less than or equal to, or is it greater than? Well, it's greater than. Can't fit it here. Is it less than or equal to, or is it greater than? It's less than or equal to. Can't fit it here. Is it less than or equal to, or is it greater than? It's greater than. So I found a home for it right here. At some point, we kind of need to stretch these guys out a little bit so you can have space for your stuff. Then we'll take our 7. Can't fit it here. Less than or equal to and greater than. It's greater than. Can't fit it here. Less than or equal to or greater than. It's less than or equal to. Can't fit it here. Less than or equal to or greater than. It's greater than. Can't fit it here. Less than or equal to or greater than. It's greater than. So we'll find its home right there. Finally, the 9. Greater than, less than. So this guy has 2 children, these 2. This guy has 1 child, has 2 children, these 2. This guy has 1 child, this one. This guy has 1 child, this one. Now this guy has 0 children. Nodes with 0 children are called leaf nodes. Get it? Trees have leaves. All right. All right. So this is a binary search tree. Even though this tree kind of looks a little bit disheveled, let's say, and it is out of balance in this case, not horrifically so, but a little bit so. It is in order. Okay, so we have followed the rules of our binary search tree and gotten things put into this, kind of like I used that example of that Plinko game where you drop something and it finds its final home, but it goes to the place, instead of it being random, it ends up in kind of like the bucket, the area that is appropriate for its value relative to its parent, relative to that, relative to its grandparent, relative to its great-great-grandparent, so on and so forth. All right, so now we have this concept called traversing a tree, or let's say traversing a binary search tree, because this really only makes sense for binary search trees. We have 3 different ways that we can traverse a tree, and I'm going to steal something here. We have in order, we have pre-order, we have post-order. In order says visit left, then self, then right. Pre-order says visit self, then left, then right. Post order says visit left, then right, then self. All right, so let's think about this particular tree and what each of these says. So in order says, so if we were to describe the nodes of this tree in order, we say, we're going to start here at the top. In order says we visit the left node first. Now, every node we hit, we are visiting that node in order. So when I say visit this node, I'm saying visit this node in order, which says he should first visit his left node. He has no left node. Then he visits himself, 0. Then he visits his right. And this right, this is not actually his right. He has no right child. Okay. Now we bounce back up and we visit this guy's self, his second step. Should sound a little recursive, right? All right. And then we visit his right child, which is an 8, but we're visiting that guy in order. So we visit his left child in order first. This guy then visits his left child, which there isn't one. Then he visits himself. Then he visits his right child in order, who visits his left child. There isn't one, so he visits himself. Then he visits his right child in order, visits his left, not one, visits himself. Visits his right, not one, bounces back up. Bounces back up, bounces back up, visits himself, visits his right child in order, which visits his left child, which visits in order, which visits his left child in order, which there isn't one. Then it visits, we're at this guy, he has his left child. This guy visits his left child, which there isn't one. I'll stretch this out. So then he visits himself. Then he visits his right child. There isn't one. Bounces up, visits himself. Visits his right child. There isn't one, so we're done. In order gave us our sorted values, did it not? These are the values in order because we visited it a certain way. We follow the rules for visiting it. All right. Pre-order says we're going to visit ourselves, then our left, then our right. So go ahead and take a minute. Given this tree, follow those rules. If I'm visiting the nodes of this tree pre-order, I will visit myself, then the left in pre-order, then the right in pre-order. So try to give me the order in which we reach these pre-order. Take about a minute to figure that out. These make excellent test questions, by the way. Hint, hint. All right, so let's look at pre-order here. So we're going to visit our self first, then our left, then our right. So this will be a 1. Then we visit our left pre-order. So we get a 0. Then we visit our left pre-order. There's nothing there. We visit our right pre-order. There's nothing there. We bounce back up. Now we visit our right pre-order. So we get an 8. Then we visit our left pre-order. We get a 2. We visit our left pre-order. There's nothing there. We visit our right pre-order. We get a 4. We visit our left pre-order. There's nothing there. We visit our right pre-order. We get a 7. We visit his left, nothing there. His right, nothing there. Bounce up, bounce up. Wait, hold on. Did I do the? Yeah, we're good. I didn't remember because my picture's a little sketch here. We did hit the 8, then we hit the 2, then we hit the 4 and 7. Okay, got it. Now we bounce back up. We visit the right in order, 12. We visit the left in order, 9. Visit his left, nothing there. His right, nothing there. Bounce up. His right, nothing there. We're done. All right, so in order, or I'm sorry, pre-order. I kept saying in order. Visiting each of these pre-order, we get 1, 0, 8, 2, 4, 7, 12, 9. Right? Okay. Why would we ever do that? Okay, and what could that be used for? Okay, probably something. I might not have asked it otherwise. Yeah, something like that. Okay, stew on that for a second. Why we might use pre-order. Let's go and do post-order now. So post-order says visit left, then right, then yourself. So we visit the left post-order. He visits left, nothing. Visits right, nothing. Visits himself. Bounce back up, visit right, post-order. Visit left, post-order. Left, nothing. Right, post-order. Left, nothing. Right, 7. Then self, 4. Then self, 2. Wait, hold on, did I miss the? No, we're good. I jumped the right way. Then right, then left, 9. Then bounce. Well, then his left, nothing there. His right, nothing there. Then the 9. Bounce up. His right, nothing there. Then the 12. Then the 8. Then the 1. Okay, so that is post order. We visit ourselves last. All right, so I'll pose the same question. When will we use this? Now, we want to think about when might you use each of these abilities, right? Okay, in order seems like maybe it's kind of self-explanatory when you need to get the values in order. Okay. Hey, our data structure is a structure for holding data, right? And this guy happens to hold data in somewhat of a weird way that's following these couple of rules, but we've seen that, you know what, I can extract my values out of this in already sorted order by calling in order on this. Make sense? All right, so let's go back to this next one, the pre-order. Assuming we could use it for something, what might we use pre-order traversal for? I mean, when we look at this output here, this seems a little bit funky, right? At a glance, does this seem useful at all? My guess is, for most of you at least, you weren't paying enough attention to the order in which I originally built this tree. But I think you'll find that this is the exact order. So if you want to make a duplicate of a tree, you can visit that tree in pre-order, and that will then get you the order in which you add these elements to a new tree to give you the identical starter tree. So if I add a 1, then a 0, then an 8, then a 2, a 4, a 7, a 12, and a 9. If I start adding those things in that exact order to an empty binary tree, I will end up with the same binary tree. I mentioned earlier that binary trees, you will get a different tree if you add things in a different order. Make sense? So if I go back in and I add these guys to a brand new tree, I'm going to get a very different looking tree than this. Okay, so pre-order supports copying a tree as maybe an obvious use. What about post-order? Go ahead. Okay, so we hit, so 0, 7 are at the, these are the bottom levels of, so hold on, I think I have this backwards. Do I not? My numbers don't look right to me. Post order, we go left 0, left, left, 7. We don't visit the 4 yet. This is out of order. Is it not? Left, right, south. Oh no, it was right. So let me just check this before I explain something. So 0, we visit this guy post order. He's got no children. So ultimately we get a 0, bounce up, visit the right post order, visit the left post order, visit the left post order, nothing here, visit the right post order, visit the left post order, nothing here, visit the right post order, visit the left post order, nothing here, visit the right post order, nothing here, visit the 7, bounce up, visit the 4, bounce up, visit the 2, bounce up, visit the right post order, visit the left post order, visit the left, nothing there, visit the right, nothing there. Then we get our 9, visit the right, nothing there, we get our 12, bounce up, we get our 8, bounce up, we get our 1. Got it. Okay. So if we do this, so this is accurate, this order we have this thing in. What could we use this for? He mentioned that he notices it hits the bottom first. So on the left-hand side, if we were to, let's think about deleting elements from this tree. If I delete the 0 first, then the 7, then the 4, then the 2 and the 9. This is a little bit misleading how I have, no, that's okay. Yeah, I could, but I maybe won't. Go ahead.
How would this work if 4 had another child?
A left child?
Yeah.
What do you mean, how would it work? For post order?
How would it affect the order?
Well, so I mean, you're saying what would happen if we got to make sure we get something appropriate here. So we need, it's going to be greater than this. So let's say it's a 2, 3 could be a 3. Yeah, so this could be a 3. A 3 would have gotten added there. So if my tree looked like this, yeah, well, then I would have just visited it differently. When I got to this level here, I said visit. So I visited this guy in order. That's my 0. I'm sorry, post order. This guy post order. That's my 0. This guy post order. This guy post order. Boom, nothing there. This guy post order. This guy post order. So before that 4, I would have had a 3.
I'm just trying to understand the relationship in the case that
well, right. So I guess that's what I'm getting at here. I mean, if the guy had a left child, first of all, the left child would have to be a legal left child in a binary search tree, right? So if he does have a left child, that would change. I mean, in all of these, we visit every single node. The question is what order do we visit the nodes in? Yeah. 3 come before the 7, but a 4, so 3 is greater than 1, it's less than 8, it's greater than 2, it's less than 4.
Yeah, and post order, was it, you visit less than 9?
Oh, yeah.
Sorry.
I get what you're saying. So it should be 3, then 7, then 4, like that. Yeah, pre-order, it's going to, let's see, the bad thing when you add things. Well, okay, I guess what's the value of adding this thing here for our numbers? I don't know that it really gives us value for our example here. So we can remove the 3. So at least now these are back to, let's say, correct. Go ahead.
If you were to add that 3 like right now, with pre-order, you type the 3 onto the added of that?
Yes. Because this is used for copying. Yep. And then in order would have the 3 right here. That's where it would naturally end up. All right. So post order can be used if we want to delete elements of a tree from bottom up. Perhaps we delete them, or perhaps we just visit them from bottom up. So really, what are we doing? We're visiting the 0 first, then the 7, then the 4, and let's see, this is level 0, level 1, this is level 2, this is level 3, this is level 4. So starting from the left, we get its most bottom level and then work our way up. So that's a 0. Then we get this guy's most bottom level, work our way up, 7, 4, 2. Then we get this guy's most bottom level. We get our 9, 12, 8, up to 1. So we are visiting as far down as we can on each branch before we start bouncing back up. So there's something when we think about searching binary search trees, we have something called a depth first search, where you look deep down in the tree for things initially. And then there's a thing called breadth first search, where you start at the top of the tree and start looking across. And depending on the nature of the values you're storing, you might decide that one of those search approaches might make more sense than another, just because of the nature of the data that you're working with. Go ahead.
So conceptually, is deleting it in the order of order, so you do it. Is that kind of like how when you delete the elements in other places, you go exactly? You don't want to delete something that is still like.
Well, let's say maybe. What would happen if we're adding this to another tree? Let's build a tree out of our post order elements. So let's see what's the best way to do that. Let's copy this. And then let me move my Legos. So we're going to, for post order, we're going to add a Ninja. We'll add a 0. Then we're going to drop a 7. 7 is greater. Then we're going to drop a 4, which will go here. Then we're going to drop a 2, which will go here. Then we're going to drop a 9. Then we're going to drop a 12. Then we're going to drop an 8. then we're going to drop a 1. So that's the tree that gets produced by this guy. This is the tree we had before. Do we have any preference between these trees? The answer could be no, but we're exploring the validity of if we did delete these values with the assumption that we might put them into something else. First of all, we have evidence here that we did produce a different tree with the same values, right? This tree right here and this tree are different trees, even though they hold identical values, right? This tree here has a depth of, it doesn't matter how you count it. So this is 1, 2, 3, 4, 5. It's a depth of 5. This guy has a 1, 2, 3, 4, 5, still a depth of 5. This tree is pretty lopsided. It's right heavy. There's nothing on the left-hand side. If we visited this in order, we would still get our numbers in the identical order that we had here. Yeah, I don't think that deleting them and then adding them again gives us any obvious value. So the idea here is if the nature of your data was such that if things were added in a certain order, where maybe the thing that was last added is the thing that is like if you're implementing kind of a last in, first outy type thing, the things that were added last are likely getting deeper down the tree as far as they can go. So if you're going to hit those things first, then you're removing things in the inverse order in which they were added. Is that a true statement? We did remove the 1 first, but because this is our duplicating, right? Yeah, that doesn't have a direct relationship. So I guess post order literally is just going to trim from the bottom up on each branch if you delete it from that. But it does allow you to deal with the depth of the tree before the breadth of the tree. I'm trying to think if there's a practical example when post order is extremely beneficial. Maybe something will pop into my head. We'll see what happens. But obviously in order makes a lot of sense. And pre-order, if you're duplicating the contents of a tree, could be very handy. Remember, we're dealing with pointers here, so you don't necessarily want to take a node and put it into another tree because now you're going to break that node's pointers, right? So if I'm duplicating this tree, I'm going to make a brand new node that is this 0, or in this case, a brand new node that's the 1 and add it to the tree, then a brand new node that's a 0 and add it to the tree, and so on and so forth. Get rid of that slide. Go ahead.
So I'm assuming that when you're creating one of these stuff, if you take one full set of data, you're going to put in that one. Or you would set up an algorithm that would categorize stuff in the right way.
Well, I mean, you don't have to take all your data at once. That's the purpose of really a binary search tree, is that as your data set grows and you add it to your data, you add it to your structure, you're always adding it in such a way that your data is still ordered. It's still organized.
Can you encounter a situation where you have to put something between a 4 and 3, for example? Like put a new parent?
Only if you were balancing the tree. Once the tree looks like this and you added something else, you can't, nothing would get inserted in here. There's no room for it. Yeah, I mean, it just follows these exact same rules. You drop a 3 on top. Is it less than or equal to? Nope. Is it greater than? Yes. Go here. Is it less than or equal to? Yes. Is it less than or equal to? No. Is it greater than? Yes. Is it less than or equal to? Yes. Drops it right here. Yeah, you don't insert in between things. You find the first home that it can drop into that follows these rules.
So then, like, you read that and follow the same rule on the left side of how to read it, and then read that in the proper way.
If you were to do in order again, right, it would be 0, 1, 2, 3, 4, 7, 8, 9, 12. If you were to revisit that tree.
Yeah, I'm just trying to like, have it all over. So.
Yep. All right, so questions about our binary search tree at the high level. Go ahead. To store data. I mean, so if you're storing information that you need stored in order, so let's think about a linked list. So when will we use a binary search tree maybe as opposed to a linked list? If I have these values here, this was the order in which we created this thing. If I added these elements to a linked list in this exact order, I'm going to be left with a linear linked data structure where there's a 1 linked to a 0, linked to an 8, linked to a 2, a 4, a 7, a 12, and a 9. That data is there, it's traversable, but it isn't stored in any sort of structure. It's not stored in a formatted way. It's not stored in an ordered way. If I do these exact same values in a binary search tree, no matter when I add a value or what order I add these values in, they're stored in such a way that the data is searchable because the data is stored in order. It might look a little funky, but if I'm looking for a 4 here, if I was looking for a 4 in this collection, right here, I would have to start here and say, is this a 4? No. 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 Actually, let's use a 9 as our better example for this guy. So if I'm searching for a 9, I will literally have to check every single bucket of my linked list until I finally find that 9. But if I'm doing a search, if I'm searching for a 9 instead of a binary search tree, I'll start here. It says, is this a 9? No. Well, if there were a 9, is it going to be to the right of this or to the left of this? It's going to be to the right. Is this a 9? No. Well, if there was a 9, would it be to the left of this or to the right of it? It would be to the right. Is this a 9? No. If there was a 9, would it be to the left of this or to the right of this? It would be to the left. Is this a 9? Yes, found it. So what we just did there is something called a binary search, which is, sometimes it's called a dictionary search, where it's effectively, you are looking for a value. What do? You go to the middle of a dictionary. You say, is this the word I'm looking for? If yes, I'm done. If it's not, you can say, well, does the word I'm looking for, does it come before this word or does it come after this word? Because dictionaries are in order, right? So if it comes after it, you rip the dictionary in half, you burn the left half. That's what I always do when I use dictionaries. I treat them as disposable items, right? Because we don't need dictionaries, we have Google. So in any case, you would get rid of the left-hand side, then you go to the middle of the right-hand side, say, is this the word I'm looking for? If yes, got your answer. If not, decide, is it to the left or to the right? Since the data in a dictionary is already stored in order, it allows us to find values in the dictionary more quickly than literally starting on page 1 and saying, is this the word? 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 Make sense? But that required our data to be stored in a specific way to allow us to more efficiently search for something in the dictionary. Yeah.
And then also, if you were looking for or something, you go like down to the 12 and then say, it would be to the left, you give it a 9, and then flip that one, you can say,
didn't find it. Yeah. So if you, until you, yeah. So this is, and really at the end of the day, there's nothing wrong with a linear search, you know, or a sequential search. Sequential search says, hey, you know, if you shuffled a deck of cards and I say find the 4 of hearts, your only option is to start flipping through the cards, right? You know, in order. There's no rhyme or reason because you've shuffled those guys. But if that deck of cards just came out of the box when it's kind of, they're usually sorted, right? Then you can kind of flip through and kind of find the hearts section, right? And then you can zip towards the beginning of the hearts section, the first third of the hearts section, and find the 4 there. So you can take some leaps through your data to shorten the number of places you have to check. Computers are really, really, really fast, so a sequential search most of the time isn't a problem, right? But if you start getting into humongous data sets, so this gets back to the idea of when would we maybe use a binary search tree. You get into these humongous data sets, maybe something like Amazon uses with their customer base or their collection of items, things like that. There's lots, right? Lots and lots and lots and lots and lots of stuff. Well, it might be in Amazon's best interest to store stuff inside of a binary search tree for like user accounts or something like that. But they indirectly do it through a database system like Oracle or something like that, or DB2 or Microsoft SQL Server. They use one of these enterprise level databases, which under the hood are implemented in terms of binary trees. You have a question? Okay, I usually do. Everything that comes out is just gold. Go ahead. You mean for binary search tree? It's built in sorted order. Whenever I drop something in, it will put it into the perfect place such that if I were to visit it in order, I would get them sorted because I follow these two rules. Okay, so next thing, we want to implement one of these guys. Who are our players in our binary search tree? If I look at any of these pictures here, we have a bunch of nodes, right? So we have nodes. And what's a node? A node is a payload. Yeah, a left and a right child. Left child. Right child. All right. We also have a root. This guy points to the top of the tree, the root of the tree. So you can kind of think of trees as upside down. Tree data structures are like upside down real trees, right? Because in real life, the root is at the bottom, right? But in this case, we flipped it upside down, and our root we find here at the top of the tree. Go ahead. Well, okay, that's a good question. So initially, just the root. But this is the difference between when we talked about linked lists, and doubly linked lists. Because what if, is what he's talking about here, is in this case, this guy knows about this guy, but this guy does not know about this guy. It's a one-way street, okay? So if I'm down at this level and I want to get back up to the level above me, can't get there because I don't know the guy above me. Now, we've kind of accidentally written trees before. They weren't necessarily binary trees, but we wrote trees when we did our dungeon crawler, right? Where we had rooms and rooms linked to other rooms. We had a list of rooms they linked to each, and really they were kind of quadrary trees, right? Then we just do north, south, east, west. Yep. So we had 4 possible children to, but that would fall there. I don't think anybody specifically uses quadrary. Is that right? Quadrary trees? Binary, trinary, quadrary. It's got to be a word, but nobody uses it. But we're gonna start using it. That would just fall into that category of n-ary trees. But typically, an n-ary tree says there is no rule to how many children any individual node has. So in a situation, if we're using our example before, where we have a child that always has up to 4, or a node always has up to 4 children, it would be a quadrary tree, I think, in that case. Did you look it up? Is this a thing? Quadrinary? Quaternary. Well, that sounds way more made up. Really? Quaternary?
Quaternary is a word for urban dictionary, but that's not a great word.
Well, quad is 4. Quadrinary, binary, bi is 2, nary, quadnary.
According to
Quaternary.
Webster Dictionary, is quaternary.
Well, that's what he just said, quaternary.
In this case, isn't a binary tree
He's talking about
the binary language is zero.
Well, yeah, those are the bits of the binary language. So what's your question?
A binary tree can have 0, 1, 2.
Correct. That's just, I mean, because it can have up to 2 children. You're trying to equate the number of children to the bits. There's no relationship there. Yeah. But actually, if we go back and you think about, so throw the quaternary trees out. We're never going to say that again now. Okay. That word is dead to us. So if we think about our dungeon crawler, would we use a tree for our dungeon crawler? And after you correctly answer no, tell me why. Okay, so why would a tree not make sense? Even an n-ary tree. Why would this not be an accurate representation or a flexible enough representation for our dungeon crawler? I think in our dungeon crawler, didn't we kind of map out the computer science department? In fact, this room is a good example of the room we're currently sitting in holds the answer to my question. Why is a tree not a good structure to hold, in that case, a map, right? Just looking around the room.
I'm trying to think of like how to bring stuff up.
What room's through that door? The lab. Is there only one way to get to the lab? Oh. So notice here in a tree, any node only has one road that goes there. That make sense? That's the nature of a tree. Yep. So to get to a 7, we could only get there through a 2. If we took this 8 and linked it to the 7, that guy's not a tree anymore. It's called a graph. Go back to our thing here. This is the last one, graph. And if we want to map, pun intended, if you want to map a graph to something that we use all the time, it's a map. So this traveling salesman problem actually is something that's like related to how like Google Maps might use to find the quickest path to their destination using, the GPS and the knowledge of all the roads and the speed limits and things like that. Traveling salesman's a little bit different than that in that it's, I'll just give you the initial idea. But the traveling salesman problem says you can have, let's assume you're a traveling salesman and you are selling things in all the nearby towns. So I need to sell stuff. Let's say my home base is Grafton. I need to sell stuff in Mequon, Cedarburg, Milwaukee, Port Washington. Those are my 5 places that I sell on a given day. And I want to know what is the best path to follow to visit all of my sales locations using the least number, driving the least number of miles, let's say, for a real example. Okay, what order do I visit the towns in to minimize my miles driven on the day so I ultimately end up back at home? That's what the traveling salesman problem says, and that's a hard problem to solve because we have to look at it through brute force. And we're going to look at a couple of different algorithms for looking at the traveling salesman problem. One of them is called Dijkstra's algorithm, and another one is min-max trees. We'll definitely look at Dijkstra's algorithm, but we might not look at min-max trees. But regardless. So a graph has potential for loops where we can have a node that connects to another node where that same node has another connection coming to it, where a tree would never allow that. All right, so binary search tree. We're going to keep track of a root node. This is the top of the tree, or the bottom of the tree, however you want to think about it, but because of the way we draw it here, the root is at the top. It's going to have nodes. Nodes have a payload, they have a left child, they have a right child. We're going to say that a binary search tree has a ability, just say abilities, which we can say are methods, right? So we'll say visit in order, visit post order, visit pre-order. Visit in order should display to the screen the contents of the tree following the in order algorithm. Visit post order should display to the screen the contents of the tree following the post order algorithm. Pre-order, the pre-order algorithm. So you can actually use visit in order to test whether your binary tree was set up correctly, right? Because in a binary tree with a node, I don't want to give away too much yet. With a binary tree, when we add stuff, we've already talked about on this previous thing, that when you add something to a tree, it's going to find the correct place for the tree, because we're always adding to the tree to keep things in order, not necessarily to keep things balanced right now, right? We're at the mercy of how we added stuff to the tree. We could probably go through this and figure out what is the worst order. We can add stuff into the tree that just basically gives us a line, right? You know, like, okay, that is a horribly unbalanced tree. It just, everything just goes to the left or something like that. 0, 1 to the right. Yeah. Yep. So if you added, if you built your tree, it would be a linked list. Effectively, it would be a linked list hidden inside of a binary tree, because you're only ever using one child. If you added them back in order, because you'd have a 0 linked to the right to a 1, linked to the right to a 2, linked to the right to a 4, right 7, right 8, right 9, right 12. That would be a very inefficient, but technically correct binary tree. All right. So the idea would be is you built a binary tree and then allowed people to add elements to the binary tree. So you're going to build the default abstract data structure. Build a generic binary tree capable of holding ints. The tree should allow you to add values and have those values automatically find their correct home in the tree following the binary tree rules. Test your tree by implementing the visit in order method, which should show a sorted list in the event that your tree was properly built. Make sense? Because if I asked you to write like a display method for a tree where you had to kind of build a tree that looked kind of like a tree, it sort of sucks. Because there's a lot of formatting and spacing, and you could actually technically make it work. In fact, way back when we still had the dot matrix printers, we wrote one of those where it would print out the things, and you would line up the sheets of paper to show your gigantic tree. But there's not really value in, formatting a text-based output for that when you can just test your accuracy of your binary tree by visiting in order. That makes some sense? All right, so for next class, from scratch, I'm not going to give you a starting point. So from scratch, you're going to have to build your node object with the proper stuff in it. You're going to have to build your binary tree object with the proper stuff in it. Have the ability to add things to a binary tree and have them get added to the appropriate place, right? And then be able to visit in order. You can write a display method that calls visit in order if you want. And what it will do is it will show you the elements in your binary tree that's the result of visiting all the elements following the in order algorithm, which should be a sorted collection of nodes, right? It should give you the numbers in order, in ascending order, which would then prove that you built your tree accurately. If you visit in order and you don't get a sorted list of numbers, one of two things is true. You either didn't build your tree right, or you didn't write in order right. One of those two things is true if when you go to display it, you don't get in order. All right, so you're going to build this completely from scratch. In the end, submit a GitHub link and a self-eval. All right, questions what I'm asking you to accomplish? Should be fun, shouldn't take that long. Go ahead.
For when we first do the binary tree, if you're looking at self, it's 4, and the value of the person is also 4.
Less than or equal to. So by your example here, let's say we're trying to add we're trying to add a 1. That's 1. So we try to add a 1 here. I can't add it here because somebody's already bought this house. That's to your point earlier. You can't just squeeze it in somewhere. So because I don't have room here, I say, well, should it go to the left or should it go to the right? Everything to the left is less than or equal to it. Everything to the right is greater than it. Make sense? So that's following these rules. So pay attention to the little equal sign on that part. Yes, because it would be 1 would go to the left of a 1, it would go to the right of a 0. It would go to the left here, right here, and then the left of that guy. Because it's less than or equal to 1. Yep. All right, so we'll write the solution in class, next class. An encouragement for doing this assignment is, like I've said multiple times, get it working first. But one thing I think you'll see, whether you stumble upon it on your own or you see it in class next time, is the algorithm for building binary trees is actually quite simple. And I mentioned a word earlier today that hopefully comes to mind when you're writing that, and that's recursive. Okay, it's recursive. But I would actually call this pseudo recursion because you're not actually calling that same object's function. You're calling an identical type of object's identical function. right? If somebody was trying to add something to me and I couldn't add it, I'm going to add it to one of my children, which are effectively the same kind of thing as I am. So I'm calling one of the same methods, maybe the same method I'm currently in. So it's kind of a recursive-esque, but generally when you define recursion, it's when a function calls itself from within itself. In this case, it's calling a very, very, very close relatives identical method type thing. But I would still call it a recursive thought process. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Thursday. You should have taken the call.
I was about to. Because I just got a vaccine secured on Saturday.
Yeah. That's your first one?
Yeah.